Hi everybody, welcome back to the channel. In this video and in the next couple of videos, we're going to look at how a function f relates to its derivatives, or maybe more specifically, what do the derivatives, the first and second derivative of f, tell us about the original function of f. Okay, in this video, we're specifically going to compare f to f prime and see how do characteristics of f prime change or determine or dictate behavior of f. What does that give us, or what can we find out about f by knowing f prime? Okay, so first of all, I just want to point out that when you're talking about a derivative and you're looking for a value of a derivative, which is what we're going to be doing in some of these, there's kind of four different possible cases or four different outcomes that could possibly happen. The first one that we could have is that it's possible for f prime to not exist. Okay. We know why f prime doesn't necessarily exist, and sometimes maybe at a specific value f is not continuous, maybe at a specific value f is not smooth. Those two criteria that we need, it's possible one of those is not satisfied. So another option for f prime is that f prime could be equal to 0. So maybe I should just say in here f prime of c. We're looking at a specific value, not just f prime of x as a whole, but at a specific value of c. So f prime of c could be equal to 0, and remember what we called this was a critical value, or critical number, and a critical number kind of actually describes both of these, because remember, critical number kind of comes from two different places, which is where does your derivative not exist and where is your derivative equal to 0. So those are possible options that could happen when we talk about finding f prime of c. The other two options that we could have, the other two cases we could have, is that f prime of c is positive and f prime of c is negative. And so we're going to actually look at kind of all four of these cases and say when f prime of c does not exist, or is equal to 0, or is greater than 0, or is less than 0, what does that tell us about our function f? Okay, so what do these tell us about f? And what we're going to try to do is relate one function to another. So what do these about f? Okay. So maybe you have an idea. We've kind of already talked a little bit about maximums and minimums, but I want us to just be a little bit careful, because just having a derivative that's equal to 0 does not necessarily mean that you have a maximum or a minimum at a specific point. Let's take a look at a specific example. What if we have a function, I'm going to put it down here in kind of a small space, but what if you're looking at x cubed? Take the derivative and set it equal to 0 and solve. If you take the derivative, you get 3x squared, set that equal to 0 and solve. What you get is x equals 0. Well, you know what the graph of x cubed looks like. Does it have a maximum or a minimum at x equals 0? No, it doesn't. Even though there's a critical value there, does not necessarily mean it's a maximum or a minimum. It could have been. We've seen plenty of examples where when you take a derivative, you set it equal to 0, you actually do get a maximum or a minimum, and that's often the case, but not always. Okay, so we want to just think about kind of what happens in each one of these circumstances with our original function f. So I've taken these from our book just so that I didn't have to handwrite out all these words, but we can take a look at the different scenarios that show up here. And our book gives these some specific names. I wouldn't care that much about kind of remembering calling it increasing, decreasing test. I don't really care. What I want us to know is, how does the graph of f prime help us understand what's going to happen on the graph of f. Okay, so let's look at the first part. Part A up here at the top says if f prime of x is greater than 0 on an interval, then f is increasing on that interval. So if I go back, that's actually kind of that third case, is what if f prime is greater than 0? I guess I put them in the other order, didn't realize. If f prime is greater than or is greater than 0, then you have a graph that is going up to the right, because if you think about the derivative as being a tangent line, remember you have the slope, or the slope of the tangent line there is positive. Okay, so you're definitely going to have a function that is increasing. And same thing for part B. If you have a function that is decreasing, then the derivative, which is the slope of that tangent line, is going to be negative. Obviously, it's going to be going down to the right. So I think both of these two, for part A and part B here, and the increasing, decreasing test, these should be fairly straightforward. Then we get into kind of some sticky territory because, again, remember earlier we said that if your derivative is equal to 0, we tend to think maximum or minimum, but that's not always the case. In fact, there's kind of 3 different scenarios there as well. So here's how I want you to think about this. If f prime changes from positive to negative, okay, think about this a second, if f prime changes from positive to negative, that means f changes from increasing to decreasing. Okay, so you're going from increasing to decreasing. That had better mean that there is a local maximum at that value of c. Okay, if in the second one f prime changes from negative to positive, that means you have a derivative or a tangent line, slope of the tangent line there that's negative. Okay, so f is decreasing and then f is increasing. That had better mean that you have a local minimum. But there's also a third case. And so it says, what if f prime is positive to the left and right of c? So if f prime is positive to the left, it means f is going up, or f is increasing. And then to the right of that value of c, f is also going up because f prime is positive again. You could have something like this. This is kind of that example of our cubic that we saw earlier where it's going up, where f is increasing, going up to the right, and then f is increasing, going up to the right. And even though there technically is a critical value there at 0, it does not mean that's a maximum or a minimum. Same thing if it was going down to the right and then down to the right, if f had that behavior. So in that last case, we don't necessarily have to have a maximum or a minimum if we have a first derivative that is equal to 0. All right, so let's take a look at an example of this. And in this example, I want to lay out a structure that I think is going to be really helpful. In fact, in the next video, when we take a look at f double prime, the second derivative, we're just going to take this same structure and just add to it a little bit and just build on it. So this structure is going to be really, really helpful. So here's what I would recommend. If you know what f of x is equal to, first of all, you should start out by finding f prime of x. That makes sense. We're looking at how those two relate to each other. So this is 12x to the third. Minus 12x squared minus 24x, and then just plus 0 on the end. Okay, so if this is, it's probably the weirdest 3 I've ever written in my life. This is our first derivative. We can set this equal to 0. And this is going to be a common strategy, common structure. We saw this back in the last couple of sections as well, is take the derivative, set this equal to 0, and solve. Now this one happens to factor pretty nicely. If you have a factor out of 12x out of everything, okay, and you're left with an x squared minus x, minus 2 equals 0. And so you can actually solve here. You can factor further. This means the first one gives you x equals 0. Let's see, the second piece factors as x minus 2, x plus 1. And those are both equal to 0, which means you get x equals negative 1 and x equals 2. So now we know where f prime is equal to 0. I told you that we're going to have some structure, that I was going to introduce some structure here that I think is helpful. And we're going to go ahead and use these 3 points, x equals 0, negative 1, and 2. And here's what the structure is going to look like. I would recommend drawing yourself a number line. I know this sometimes feels a little trivial because number lines feel like a long time ago, but this is going to be really, really helpful for us as far as organization. I'm going to go ahead and put these values in the number line, negative 1, 0, 2. And what we're going to look at is what happens with f prime of x, and then that's going to hopefully tell us what happens with f of x. Okay, so we know that if you plug in these values into f prime of x, what you're going to get is you're going to get 0 for each of those. So f prime of negative 1 is 0, f prime of 0 is 0, f prime of 2 is 0. Really the question is what happens on the intervals between those numbers? Okay, or I should say less than negative 1, between negative 1 and 0, between 0 and 2, and between 2 and infinity. What happens on each of those intervals with f prime? And if we know how f prime behaves, really as far as is f prime positive or negative, that's going to tell us about how the function f of x behaves. So this is the structure we're going to use when we look at second derivatives. In the next video, we're just going to take this structure and just kind of build on this a little bit and add to this a little bit. So let's look at what happens if you plug in a value further to the left of negative 1. I'd recommend go ahead and plug in negative 2, and you plug that into your f prime function that we had up here, I think what you're going to end up getting is that you're going to have a negative. I don't actually remember what you get as a negative number, but the crazy thing is we don't actually care what negative number I get. All I care is that we get a negative. Because if you remember from our statements earlier about what does f prime tell us about f, what does it mean when f prime is negative? It means that f on that interval has to be decreasing. And I like to draw a little picture in here. It says decreasing. I tend to be visual, so I put a little picture on there of a function that looks like it's, or a little piece that looks like it's going down to the right, just so that I kind of have an idea of what that looks like. If you go ahead and plug in a value in between -1 and 1, how about -1/2? Seems like a pretty good choice. There's no whole numbers in between there, but plug that into f prime. Okay, I think what you'll find is that you end up getting a positive, and I don't actually care what positive number I get, I just care that it's a positive. Because if f prime is positive, what does that tell you about f of x? Well, it means on that whole interval, f of x has to be increasing. So again, I like to put a little picture on here. You don't have to put the picture, I just like having a little visual aid. And then go ahead and plug in a value between 0 and 2. 1 seems like a pretty good choice. And if you plug in a value of 1 into f prime, what you're going to get is a negative number. And I know because I did it, and not just because it goes from negative to positive to negative. That doesn't always happen where you kind of alternate negatives and positives. It does seem like that's the case in this example, but that doesn't happen every single time. In fact, earlier we saw that one of our cases could be that on either side of that value, you might have f prime being positive on the left and positive on the right, and that's a different scenario. So here, when you plug in x equals 1 into f prime of x, I think you get a negative, which again means that f of x is decreasing, going down to the right. And then if you plug in a value bigger than 2, maybe pick 3 or something close to 2 there, what you're going to find is that f prime of x is positive on that interval, which means f of x is increasing and going up to the right. And you'll see kind of why I like this structure is because it tells us a lot of information in a pretty concise way. It tells us the x values that we have as both our critical values down here, as well as our values that we tested down here. So you can make a distinction with those somehow if you want. If you want to underline some and highlight others or put a box, sometimes what I'll do is I'll put the critical values on the bottom of the number line, and then I'll write the other numbers up at the top, like 3 up here, where I'll write that in a different spot as a test value, just to represent that that's where that came from, that it was a test value. But then we're told a lot about how f prime behaves on different intervals and at specific values. And then in this, we can see how f behaves with decreasing, increasing. And the nice thing about having these arrows in here is it gives us kind of a visual aid to say, okay, if f of x is decreasing and then increasing, what does that mean about the value of x equals -1? It's got to be a minimum, at least a local minimum. We don't know about absolute, by the way, but at least a local minimum. Okay? If f is going from increasing to decreasing, well, then x equals 0 right here has to be a local maximum. If f is going from decreasing to increasing, what can you tell me about x equals 2? Well, that's got to be, again, a local minimum there. And so this helps us understand minimums and maximums. The structure helps us understand where f is increasing and decreasing, and helps us relate f prime to f. So we're going to use this structure in a lot of different problems. And by the way, I think if you look back at the question said, find where f is increasing and where it is decreasing. We've actually kind of answered more than just that question, but if you look at where f is increasing to decreasing, f is increasing on the interval from, let's see, increasing on this interval right here from -1 to 0, and it's also increasing over beyond 2, so to the far right. So union 2 comma infinity, if you want to write it in interval notation. And so you could talk about where f is increasing and decreasing just by picking out the different intervals.